Welcome back, everyone. In part 3 of this coding regression lecture series, we're now going to explore the wide variety of algorithms left. That includes decision tree regression, support vector regression, k-nearest neighbors regression, and random forest regression. Luckily, we can check all of these quite quickly with our run model function. Let's head back to the notebook and just explore the behavior of these wide variety of regression models available to us. Okay, here I am back at the notebook where we left off last time. We saw that linear regression only produced a straight line, and if we knew the limit scope of our X feature set, we knew, for example, that we were only going to go from 0 to 100, then we could easily see that a certain degree polynomial was also just fine. However, if we don't know how far the signal needs to extend to, then we're actually not sure whether or not this is going to be a good fitting model. So let's explore what something like k-nearest neighbors regression looks like, which we didn't actually get a chance to when we discussed k-nearest neighbors. To perform a k-neighbors regressor, we simply say from scikit-learn.neighbors import k-neighbors regressor. And then in this case, we can actually do a little for loop to see how the citing of a k-nearest k value is going to affect our predictions. So we can say k values to test out. We'll start off the nearest neighbor, and then let's go 5, and then maybe even up to 10. That way we can see the differences. And we'll say for n in k values, or for k and k values, the model will be equal to k-neighbors regressor, where the number of neighbors is equal to n. So we're going to test this out by just going with the nearest neighbor, the 5 nearest neighbors regression value, or then the 10 nearest neighbors continuous value. And then we're going to run the model itself. So in fact, we can just copy and paste this from up here, come down here, and then copy and paste that. We just need to change pipe to be model. So you run that, and we see the performance metrics here. So this was for a k value of 1, or a neighbor value of 1, k value of 2, and k value of 3. But it's probably more clear what the actual behavior is like when we see it visually. So we can see here for a k value of 1, you get this sort of very noisy high variance, but it is fitting to the curve. What's happening here is it ends up picking up a lot of these noise, trying to fit to all these points. But as you begin to average out to a higher k value, you introduce more bias. So you're not going to be fitting to as much noise in your model, and you're going to be estimating that curve a little better. As we can see, we can go up to 10 here, and we start to get kind of a smoother model. And you can expand on this by doing something like, let's just do it for 20, or for 30, or something quite large. So if I say k then is equal to 30, run that, you can see that it's trying its best to fit to the model. However, if you introduce too high of a k value, it'll become too biased, and then it ends up flattening out instead of picking up those downward curves towards the end of those signals, so towards 0 signal or 100 signal. So there is a balance there, but that's the behavior you can expect for k-nearest neighbors. Noisy, and then more bias as you introduce a higher k value. You introduce too high of a k value though, you'll get too much bias in your model. Similarly, for a decision tree regressor, we can run the similar analysis, except in that case, we're simply going to say our model is equal to a decision tree regressor, which we're going to import. We'll say from scikit-learn tree import decision tree regressor, run that, and let's create an instance of that model, decision tree regressor. Now keep in mind, a lot of the stuff that we've already talked about is available for us here: minimum sample split, leaf, max features, etc. But we're not going to worry about that too much because we just have one feature. So there's not a whole lot we can really mess around with the hyperparameters there. Going to run this, and we can see the sort of behavior that a single decision tree will have. Very noisy, picks up the data. It's very similar to having a very small k value for your k nearest neighbors. Now let's check out support vector regression. Support vector regression is a little trickier because recall we have to choose a c value and a gamma value. So for that, we pretty much always have to run a grid search when it comes to support vector machines. So we're going to say from scikit-learn.svm import SVR, which stands for support vector regression. So after running that, we'll also import from scikit-learn.modelSelection import grid search CV. And in theory, you could have done a grid search with CV for any of the models we just presented, but this one is almost a necessity because it's hard to know the default hyperparameters are going to be right or wrong for an SVR or any support vector machine. So in this case, we're going to say grid is equal to grid search CV, and we need to create an instance of our model and create a parameter grid, which means I need to say SVR is equal to an instance of SVR, and then decide on the parameter grid that is going to be acceptable. And go ahead and review our support vector machine lectures in case you're confused on this. But for my C values, we'll go ahead and start off small, something at like 0.01, and then slowly increase it, and then maybe go up to 1,000. And then for the gamma values, you can also recall that I could choose these manually, or I can just pass in the values auto or scale to test both of those out. And then for the grid search, we simply pass in SVR, the instance of the model, and then the parameter grid that we're going to be testing out. So once you run that, this grid object is going to perform cross-validation, and you can train it just like any other model. So we simply say pass in that grid here. So this is going to be support vector regression. And when you run this, it's going to take a little more time, but eventually it'll pick the best model to perform predictions on the X test set. And you notice some interesting behavior here. Due to the way support vector regression works, it's trying to keep that margin so that it best fits that curve. So it tries its best to balance out, not picking up too much to the noise. And that's where you could continue to adjust things like C and gamma, depending on how smooth or how biased you want this. But overall, given that it's support vector regression, it's actually performing quite well. Maybe not as smooth as something like the polynomial order, but you can see how this is trying its best to determine a lower variance model given what it knows from the data. And then finally, let's go ahead and explore the random forest regression, which we can easily do by saying from scikit-learn.ensemble import random forest regressor, and then we simply create an instance of that random forest regressor. So I will say RFR is equal to random forest regressor, and this is where you can play around with the number of estimators. It won't make a huge difference here really because you just have one feature. So even if you do something like 10 versus 20 versus 100, you're not going to see any major change because it's just a single feature you're really predicting off of. So we can just do something like 10 estimators for our model, and let's go ahead and say run model. We should be able to copy and paste that from before, and instead of pipe, I'm going to say RFR. Run that, and you notice similar behavior to a single decision tree here. It's going to be similar because it's just one feature, but you'll notice that same idea. It's kind of picking up quite a bit of noise, but overall, it is doing its best to fit to that general curvature. So kind of interesting that it's able to both fit to that noise, but have enough bias that it is fitting to the general curve. And depending on the situation, how many features you have, you can always compare these test metrics to something like your polynomial order to decide whether it's worth it to switch to something like random forest regressor or stick to a polynomial. It really always depends on your exact data set. Now, we're going to be covering boosting, that is gradient boosting and AdaBoost, in the next series of lectures, in the next section of the course. But let me just show you right now what they would look like if you were to perform gradient boosting regressor or AdaBoost regressor. And we won't explain how exactly they work since we're going to do that in the next section of the course. So we can say from scikit-learn.ensemble import, and I can import gradient boosted regressor as well as AdaBoost regressor. So we're going to be exploring gradient boosting and AdaBoosting, what boosted trees are in general. And gradient boosting, keep in mind, it's actually a general term. It doesn't have to specifically be for boosted decision trees, but we're going to say model is equal to an instance of gradient boosting regressor, and let's go ahead and run that model just with the defaults to see what kind of behavior it does. And running that, you should see again similar to decision tree behavior or random forest behavior, where overall it's actually performing quite well to the general shape, and this one in particular is not picking up as much noise from the data versus something like random forest, which means there's actually a lot of potential here in boosting outperforming random forest sometimes. And let's go ahead and do an AdaBoost regressor as well. So we can say AdaBoost, run that, And you can see a similar behavior here, where we're starting to pick up that general curvature. And notice it's not picking up as much of these high points or these low points. So those are boosted trees, and what we're going to do in the next section of the course is discuss boosting in a lot more detail. But I hope this overview of comparing the different regression tactics you have is helpful to you. That way you can test many models and compare their metrics against each other to decide which is the best option for you. Thanks, and I'll see you at the next section.